I'm Jack ReVelle, and this is Continuous Improvement Television, CITV. Welcome to our first telecast for the year 1995. Today my guest is Steve Ungvari, the president of the American Supplier Institute International, ASI-International. I'll be introducing you to Steve in just a minute. Before I do, I'd like to review with you the cast of characters and their topics that will be participating in this series for the remainder of the first half of 1995. Next month, March 13th, we'll have well-known author, lecturer, and consultant Peter Schultes talking about teams and why we work together. The following month, April 10th, 1995, we'll have well-known personality and chairman of Conway Quality, Mr. William E. Conway, Bill Conway, who will be talking about what every CEO needs to know about quality. Then, in May, a very special treat, Mr. Shin Taguchi, who is now the president of the American Supplier Institute, will be talking with us about using robust design and the loss function for variability reduction. And as a special surprise treat, Shin happens to be in the studio with us today. And there's Shin. Shin, would you like to say hello to the audience?
Hello, everyone. I hope I see you in May.
Thank you. And we pan the rest of the audience, except we don't have a big audience today. We rarely do. We try to work these in a kind of a closed kind of studio. And finally, rounding up the telecast series for the first half of 1995, on June 12th, that eminent, preeminent statistician from England and now the United States, Dr. George E.P. Box, who will be talking about experimental design for quality improvement. A first-class series we've got between Steve Ungvari, Peter Schultes, Bill Conway, Shin Taguchi, and rounding off with George Box. That's the first half of 1995. If, ladies and gentlemen, as you are watching this telecast today, you are moved to say, gee, I hope this continues on for quite some time in terms of the series, would you please be nice enough to give a call to NTU and let them know. A decision needs to be reached very shortly with regard to shall the series Continuous Improvement Television continue on after the first half of 1995. They'd like to know what you're thinking. And to that end, we have several phone numbers. If you'd like to phone in your ideas, your thoughts relative to your receptivity to the concept of CITV, the phone number is 1-800-964-7896. And if you choose not to call in but would prefer to fax in, the fax number is area code 810-762-9935. By the way, that same phone number and fax number should also be used if you have a question or a comment, a thought that you'd like to provide to us during the course of this particular telecast. This, as you well know, is an interactive show. If Steve or I say something that you would like further comment on or some amplification, feel free to call the phone number or to send in a fax. You can identify yourself and be heard on the air if you choose. If you prefer not, then what I would suggest is that you call in and say you'd just like to leave a thought, a comment. They will bring it to us and we'll read it over the air without identifying the source. We would prefer, of course, that we get you on the air so that you can, we get the true voice of the customer. Rather than translating it through a second and third party, we'd like to hear what you've got to say, when you've got to say it. So feel free to give us a call at your convenience. And now, it is my singular pleasure to introduce my first guest for the 1995 first half of this series, Mr. Steve Ungvari. Steve and I have known each other about 5 years. By way of background, Steve is originally native to Hungary, came over to the United States when he was about 8 years old via Austria. That was in 1953. His dad, who was a government official over in Austria, a college-educated government official, ended up with his family in rural southern Illinois, where his dad became a foundry worker, a unionized foundry worker. And Steve picked up this work ethic from his family, started picking strawberries when he was 10 years old, worked his way through school, finally graduated with his bachelor's degree from Ohio University in Athens, Ohio, with a degree in industrial engineering and a minor in mechanical engineering. Like myself, he's former Air Force. He spent 5 years in the Air Force as a pilot, as an aircraft commander on a KC-135. Since 1972, he has been a civilian. Started out with the White Motor Company as a interior trim designer, and ultimately got into quality engineering, his first exposure to quality as a profession. An extensive amount of auditing experience. Then in 1980, when White Motor Company went under, no fault of Steve's,
Nice.
he joined the Excello Corporation, a part of the Textron organization, where he became a material manager, worked very heavily in the area of SPC, just-in-time, MRP, and in general, the improvement technologies. Then in 1987, he made the big move to the American Supplier Institute, first as an instructor in the area of just-in-time and then quality function deployment. Since 1981, he has been the president of ASI-International in Europe. That's not 1981, that's 1980. I got that wrong. What year did you become president of ASI International?
About 1990.
1990. I don't know how I got that in there. Sorry about that, folks. In 1990, Steve became the president of ASI International, which covers Europe and South American activities. His major clients reads like a list from the Fortune 500. This is a man with a lot of education, a lot of experience, a lot of know-how. It's my guest to introduce you to Steve Ungvari. Steve, great to be here.
Thank you very much, Jack. My pleasure really kicking this series off, so I hope I do it justice.
I know you will. Steve and I spent quite a bit of time yesterday together talking about TRIZ, and he helped me to understand it even more than what little I had gained before. And I'm going to turn this kind of over to Steve now, and Steve's going to be talking to you about a problem-solving technique that is so new to most of us here in the United States that I think it would be safe to say there's probably less than 1,000 people in the United States that have any idea that TRIZ even exists, and perhaps less than 100 that really have a working knowledge of it. So with that, I'll turn it over to Steve. I'll ask some questions periodically, but this is Steve's show. Run with it.
Okay, thanks, Jack. Well, let's start off. There's our title slide, Problem Solving from Russia with Data. And just to begin with, we'd like to go over the program that we have today. I want to take a little time and talk about the need for innovation. It's always important for companies to be innovative and to bring new products to market. So we're just going to spend a little time about that. Then some of the typical approaches that we see to innovation. And we'll talk about a number of those and some of the shortcomings of those typical approaches. I'm going to give you then an introduction to TRIZ, where we're actually going to get into the subject matter, and then the basis for TRIZ. What are the fundamental underlying principles of TRIZ? And that's the fifth section. And then the tools and the operators. And so if the above subjects are the what's, the tools and the operators really are sort of the hows and how you actually do them in TRIZ. And then integrating TRIZ with QFD and robust design.
Okay, let's be careful, Steve. We can't assume that everybody out there is familiar with QFD. So when you speak of the what's and the hows, I should point out that what's and the hows are the basis of the house of quality, the introductory matrix of quality function deployment, where what's are the voice of the customer and the hows are the things that the organization does to respond to the needs of the customer.
Right. Thank you very much. Appreciate that. Okay, so first of all, on this whole subject of the need for innovation, maybe I ought to preface my remarks too by saying, you know, TRIZ is a Russian acronym that stands for the Theory of Inventive Problem Solving. And so if they were Russian words, we would see TRIZ. There's another acronym that we're also going to be seeing from time to time, TIPS, T-I-P-S, which is the English acronym, Theory of Inventive Problem Solving. So I'll be using those interchangeably through the discussion, maybe just to sort of set things up. But let's talk a little bit about the need for innovation. The first point that I'm making there is form follows failure. Now, most of the time people say form follows function, but it's really failure of function to perform adequately in the hands of the customer that creates the need for products to be modified and or redesigned. And interesting that I did some analysis and some research from this book, The Evolution of Useful Things by Henry Petrosky. But anyways, he mentions in here how the fork got its tines, and that's because a single-pointed instrument was insufficient for properly securing a piece of meat or a piece of food, and so over a period of time it evolved, and now it has 4 different tines in order to adequately secure a piece of food. So things evolve.
Steve, let me have that book for a second. I'd like to get it on camera so those people who might be interested in acquiring a copy can show it. I want to hold this up. If you folks in the control room can come focus in on this for a second.
If you can just put it on the overhead.
On the overhead, you got it? There we go. Can everybody see that? The Evolution of Useful Things by Henry Petrosky. And let's see if it's got...
Page 13. If you turn to page 13, you'll see the little...
Yeah, I just wanted to tell the folks where they could get it if they wanted to. It's a vintage book, which is a division of Random House in New York, if you're interested in that particular information. And moving over to page 13, what Steve was just talking about.
Yeah, what you see there is some knife fork sets from the early 1600s and an evolution of them. And what you see is two-tine forks. Well, those two-tine forks were not really adequate to properly secure food, and so what happened, as the companion to the fork, the knife developed that bulbous nose, if you will, or that protrusion in the end, and that was there in order to help shovel food in one's mouth. Okay, now if you turn over one page, what you'll see is as time goes on, the fork went from 3, then back to 2, and then finally to 4 tines. And then what happened is in that knife, that bulbous protrusion disappeared because it was no longer required. Okay,
right.
So that's essentially what we're saying. The products evolve or change because they fail to deliver the proper function in their original design.
And TRIZ is a technique, I'm assuming then, that we're going to be able to use to help us to understand how we got to where we are and perhaps even predict where we will be.
Absolutely, and to predict the future evolution of products. Okay, so continuing on that same thing, form follows failure. We see here that typical life cycle curve, and all products, you know, once they make their emergence, go through a very similar sort of development. In other words, they come up a maturity, or they come up a development curve, and then they hit maturity, and then they decline. It's a very typical life cycle kind of curves. And these are new paradigms, and you know, we're all familiar with Joel Barker and his work with the word paradigms. You know, they're patterns of behavior that establish boundaries. And so new paradigms are created all the time because there is a need that exists. Again, on the need for innovation, some companies like 3M, very innovative company, as I'm sure you're aware, 30% of their revenues, if not more now, you know, are from products that are less than 5 years old. And this is something that they track very, very closely. So we need to have new products that we need to take into the marketplace because those are the future dollars that are going to keep the company alive. There are geopolitical changes, and certainly you know this from your work in the defense industry and the commercialization of the defense industry that's going on. So we need innovation there. There are many contemporary needs. We have various technological problems. Jack, we have warranty problems. We have TGW, that's an acronym for things gone wrong. We have performance issues. We have ecology, and the list goes on and on. So there's a tremendous need for innovation. Now, what's the advantage of having innovation? If you take a look at time versus innovation, all products become better over time. I mean, as we saw in the example of the fork.
Right.
Now, as we come up that continuous improvement blue line there, if all of a sudden we get a step change in innovation, that white step change there, then essentially what does that buy for us, Jack?
Time.
It buys us time. Okay, in this town, in the Detroit area, there was one sterling example of a company that introduced a product and had the marketplace really to its own, and that was Chrysler Corporation with the minivan.
Right.
And for that period of time, everybody else was scrambling to catch up. So you need continuous improvement as well as continuous innovation in your organization. The Intel people continually introduce new microprocessors, and every time they introduce a new microprocessor, everybody else scrambles to try and catch up. But for that period of time, Intel has got the marketplace.
Right.
They've created the competitive space, if you will. Okay, so we need those. We need innovation as well as continuous improvement. Now, some of the new paradigms, just very quickly, that we've seen in our lifetime, and that are still here, and some of them have changed radically. Charles Goodyear, vulcanized rubber, George Eastman, celluloid photography, Alexander Graham Bell, the telephone, and what's really happened to the telephone. We see a lot of the rules and laws of TRIZ that we're going to be talking about in the telephone. Chester Carlson, the Xerox machine, Stephanie Quallick, Kevlar, and Jack Kilby, the integrated circuit. So we see new paradigms all the time. Now, how do we come up with new paradigms? That's the question of the next slide here. If we take a look at the level of difficulty, and the numbers I have there on the bottom says that if we have a situation where it's very, very difficult, we have a problem that's very difficult, for example, like trying to find a cure for cancer, we would say that that's a level of difficulty of a 5. That the
on a 1 to 5 scale.
On a 1 to 5 scale, right. That the time and resources needed, that's the red line that goes up, you know, is greater and greater when we have a very, very difficult problem. And then the red line coming down is the certainty of any one solution. Okay, so if it's a relatively easy problem, the certainty of any one variant or any one solution is probably pretty high. But if we have a level 5 problem, something like a cure for cancer or for AIDS, then the certainty of any one solution is very, very low.
You know, based on what you've said on the importance of innovation, breakthrough technologies, I'm starting to wonder about the future importance of Kaizen, of continuous improvement.
You know, it's always going to be important because you need to continually improve your product, and some of the breakthroughs come at different points, but you need both, and that's the message, that there isn't a dichotomy between continuous improvement and innovation. You need both of them.
Okay.
All right. Now, back to our curve here. So when we're using TRIZ or TIPS, what we're going to find out is that essentially we can change the slope of the lines. In other words, the black line coming down means that the time and resources needed to get to a level 5 solution would be much less, and then the certainty of any one solution also is going to be greater. Okay, so that's essentially the message of using a methodology like TRIZ or TIPS. It's going to change the slope of those lines. Okay?
I'm with you.
Let's go. All right, now, the innovation lever. If we're looking for leveraging in our organization innovative solutions, if I have my knowledge, I'm at a certain point away from that fulcrum, and I can apply all the leverage that I personally can apply. If you and I are working on a problem, or you, Shin, and I are working on a problem, then you know, we've got more knowledge.
But we're still in trouble.
But we're still in trouble. We have to get my wife in there, you know, to be able to help us in, right? But if you can imagine, if we had, in essence, the knowledge of about 1.5 million inventors, okay, and we're able to harness their brain power to be able to leverage the situation, then we would have a tremendous amount of leverage. And that's essentially what the TRIZ is going to do.
I think that's an understatement, a tremendous amount of leverage. 1.5 million inventors literally at our fingertips?
That's the database that is contained in TRIZ, is the analysis of 1.5 million, if not more, patents that have been abstracted into a set of laws and principles.
Okay. When you say database, that would lead me to believe that there may be some software involved with this. Is that right?
Yes, there is software, and we can talk about that probably later on. But
terrific. Okay, great.
So we need to leverage. We need all the leverage we can get, right?
You bet.
All right, now typical approaches, we said we talk about that. There are psychologically based approaches, brainstorming, nominal group techniques, and synetics. Essentially, any of these, Jack, the assumption is that within the deep recesses of the mind, the solution is there, and it's just a matter of rummaging around and finding the solution by whatever means.
And you know, in simpler times, in years past, that was probably true.
It was okay. You could get by.
Yeah.
But things have changed.
Very much so.
So then we went to more logically based approaches. For example, regular problem solving, 6, 7, or 8-step problem solving methods. Then we have the Edisonian approach, trial and error, and then another approach, morphological, which was developed by a Swiss astrophysicist, but more logically based approaches, okay? So, but none of these are necessarily totally scientific, and that's what we're going to be getting at when we talk about TRIZ. Well, there's always some barriers to innovation. And one of the main barriers is what is called psychological inertia. You know, we get trapped by our own paradigms. You know, the laws of physics, Newton said a body at rest tends to remain at rest unless it's acted upon by an outside force.
That sounds like me on the weekend.
I know the feeling. But so we get trapped in our own paradigms and our own psychological inertia, And then there's lack of knowledge. Maybe, you know, we don't know what we don't know. Or maybe the enabling technology has not yet emerged. It's not available. There are system constraints. Sometimes we don't have the time or the budget or the resources, and these could be barriers to innovation. And then the old NIH, or not invented, if somebody else thought of it, can't be good. Now, that's a disease I've seen rampant in U.S. industry, unfortunately, but there's always NIH. Now, what are some enablers to innovation? First of all, being objective and innocent, looking at things in an objective way and having childlike innocence. Examples and analogy. You know, I mean, there's an old saying that one peek is worth 1,000 finesses. When we see an example of an innovative product and or service, we can learn a lot by just benchmarking and observing. And then there's the methodological methods like TRIZ or TIPS that will get us into these analogies and these examples. And that's essentially what we're going to be talking about today.
Okay, so just for the audience again, TIPS is the theory of innovative problem solving, and TRIZ is the equivalent acronym using the Russian language.
In Russian.
Okay, so people can use either term and be correct.
Right.
Okay.
Absolutely right. Okay, so let's give you an introduction as to who developed this. Developed by Henryk Altshuler. He was a Russian. He was a brilliant inventor. He made his first invention at the age of 14, degreed in mechanical engineering, as you can see, and so he's got to be a good guy. Published numerous books and many, many technical articles. He's really taught thousands of students. And so he developed the whole sort of basic underlying need for, or the basic theory of TRIZ. This happened in 1946. He was tasked with studying patents from the world's patent libraries. So in the Soviet Union, these are not just Soviet patents. These are patents from Germany, from Japan, from the United States, from Europe.
Now, it's not clear to me. You say he was tasked. And he was in Russia at the time. Was he tasked by the Russian government, or was he tasked by some private enterprise? Who gave him this assignment?
It was the Russian government that gave him the assignment, and it was essentially to look at the patent database to see if there were any strategic technologies contained within the database of patents that the Russians, worldwide, that they had to understand and know.
Okay.
And so Altshuler then started to look at patents, and he started to classify them not by the problem, but actually by the elegance of the solution contained in. And then he started to notice some similarities as he started to cull through about 400,000 patents.
Kind of like a continuing affinity analysis.
Absolutely.
Okay.
Absolutely. So, as I said, they were reclassified not by difficulty, but by the elegance of the solution, and then this natural pattern or construct started to become evident to Altshuler.
Are you going to talk any more about elegance and what, in terms of what that means?
Yes, we'll talk about ideality and elegance.
Okay.
What he noticed in a macro sense, if you take a look at something like a ship or an airplane or an engine or any large system, in a macro sense, these systems exhibited a very predictable and repeatable morphology. In other words, they changed in very similar ways, and he found this out by studying the patents that have been applied for within a technology, for example, like airplanes. And so he wrote to Stalin, and Stalin became incensed and thought that this was, you know, absolute hogwash, and so in essence had Altshuler imprisoned.
In essence, you know, that means he really did.
He really did, yeah.
Okay.
Yeah, I mean, he was imprisoned in the gulags, and so they stuck him in the gulags where they had some of the best and brightest minds in Russia, and there he was able to practice his theories along some very, very bright, intelligent people. So he was imprisoned in 48. He was released after the death of Stalin in 1954. And it was, even then, it was, TRIZ was suppressed as bourgeoisie hocus pocus because the communists did not in any way favor creative thinking. So...
and yet that's inconsistent, if I could interrupt, with their space program, which obviously had a great deal of creative thinking, and their nuclear weapons program.
And that's where you find out that the TRIZ was primarily applied. When they really got stuck for a problem, they would bring in TRIZ specialists. So it was sort of an underground movement within the Soviet Union for a long period of time. but a very dedicated movement of people that would continue to study patents and continue to evolve the theories, and it's still evolving today.
Do they have like a professional society or anything like that?
There is a TRIZ association, and it meets, they have an annual conference in St. Petersburg, and so and the work is ongoing, the research is ongoing.
How old is Altshuler now?
I believe he's 68 or 69, still alive, located north of St. Petersburg, and not in very good health, from what I'm told, suffering from Parkinson's disease. But what happened essentially after 1985, when perestroika happened, was many of these scientists immigrated to Israel and then to other free world countries. And so we see TRIZ is now practiced in Finland, Holland, Germany, and really now in the United States for about the last year and a half or so.
Statistically, how would you evaluate the number of people that are sufficiently knowledgeable in TRIZ in the United States today that they could provide training or assistance to people who wanted to learn more about TRIZ?
A very small number.
Under 100?
Yeah, under 100, very much. There are a number of TRIZ practitioners, obviously, in the Soviet Union, but many of them don't speak English. There are a very, very small number of folks that really know about TRIZ and can teach it here in the United States. Let's go on. So let's look at the basis for a TRIZ, or TIPS theory of inventive problem solving. What we have there is the light spectrum, and the visible light band that we can see in the middle. That would be analogous to the patents that Altshuler looked at. And then from those visible things that he saw, we can extrapolate both sides of the light wave spectrum and understand. If we understand what's going on with visible light, we understand what's going on with ultraviolet light and with radio waves. I mean, you know, we can make some extrapolation in physics.
In either direction. Yeah.
In either direction. And essentially, that's what you can do with TRIZ. So by looking at what has happened in the past in patents, what does that lead you to believe you can do?
Now, if I understand correctly, this work that we're talking about was conducted originally by Altshuler, has been extended by others.
Yes.
Apparently, in the developing of these various categories that you made reference to a little while ago, various patterns were forming. As the additional research that has followed Altshuler's original work continued the same patterns, or have the patterns changed any?
There's a tremendous amount of stability in the laws or the principles of TRIZ from the original research. But the ones that were discovered initially are still there, and they haven't changed much, but there are new patterns that are emerging.
Supplemental ones.
Supplemental
Okay.
ones. Yeah, exactly right. But my question, remember, was if we can look backwards in time through patents and see what created invention, what can we do? We can also look forward in time, and that's the essence of this slide. And that's one of the elements of TRIZ, has the ability to do technological forecasting, which is, we're going to be talking about that a little bit later on.
Okay, if I could offer an analogy, if I hear you right, it's like things that we do with the periodic table of elements,
Right.
Where you, based on our knowledge of elements that have already been discovered, isolated, we are now able to forecast new elements that are likely to be discovered and show exactly where they will be placed within the periodic table.
Absolutely.
So this is the same kind of thing.
Similar thought, similar kind of thing. Okay, we're going to go on. All right, so how did all this come about? Well, it was through categorization and classification of what was found in the database. So by analogy, if for example we were to take a look at the study of chess and chess theory, if we were to look at beginning chess players, we wouldn't see any patterns. But if we went down to experts and grandmasters, we would see excellent execution, and many, many various patterns and theories of how to play chess would evolve from the compilation and study of hundreds and thousands of games of chess, okay? And once in a while you get a Bobby Fischer, who's a once-in-a-lifetime phenomena, okay, that comes with total new ways of playing the game and destroys, you know, all the other grandmasters.
Sure.
So it's the same thing with the study of patents. It was, you looked at the good patents and you're able to see very elegant solutions emerge over and over again, or patterns of emergence of solutions.
You know, I might add, for those of you who are watching the show right now live, if you have in your audience design engineers, that's terrific. If you don't, I go scramble and get some design engineers because it's becoming more and more apparent to me, and I hope to you, that the people in your organization that have responsibility for design of products and processes, robust designs of products and processes, they need to know more and more about TRIZ or TIPS. And if they're not here in the audience watching, scramble, give them a call on the phone and get them over here to watch this, because I think you're going to find that they're going to have some very interesting things to see based on what Steve has said so far.
Okay, thanks. Yes. All right. So, a classification of inventive solutions created this, excuse me, mosaic, as well as a logic that allowed for the germination of the TRIZ theory. It was finitizing and grouping and classifying all the solutions. Now, this is nothing new because we've seen the same phenomena in the natural sciences, life sciences, anthropology, archaeology, engineering, and any of the social sciences. We group and categorize things, and then we see natural patterns emerge, whatever we happen to be working in. Okay, so the initial research was conducted on 400,000 patents. Now, 90% of those patents contained no real invention whatsoever. It's only about 10% or 40,000 of which contained some level of inventiveness.
90% of the patents didn't deserve to be patents?
Well, they were system descriptions. They didn't contain an invention. I can't comment as to whether or not they deserve to be patented or not. But they were descriptions of systems. They didn't have an invention in them. Today, that patent database, as I said, has been extended to include over 1.5 million inventions, and this database is continually updated. You know, as new patents come out, they're analyzed, and if there are new theories that start to emerge, they're added into the TRIZ theory.
Who's doing this updating of the database?
The scientists in Russia and also here in the United States, the ones that have come here to the United States.
But it's still a Russian-based phenomena.
Yes, for the most part. All right, now, as I mentioned, the elegance of the solutions were classified on a 1 to 5 scale. So within the 40,000 patents, the ones that had some invention in them, Altshuler used a 1 to 5 scale. So a level 1 was a very, very simple solution achievable through normal engineering. No invention whatsoever. If I had to calculate, for example, how much paint it would take to cover my house, I could get a formula for coverage and then figure out how many square feet I had, so on and so forth, and then know I had to buy 7 or 8 gallons.
A parameter estimation procedure.
Absolutely.
Okay.
So no invention whatsoever, very achievable through normal engineering. A level 2 now is a system improvement. In a level 2 solution, we see that there could be a number of prototypes or variants that were considered, okay? And it is an in-paradigm solution. In other words, it is using the same technology but advancing that technology to a higher degree of capability and or functionality. It's an in-paradigm solution. So if a level 1, for example, I might have to figure out how much pressure I'd have to have in order to deliver fuel to a combustion chamber. That'd be a level 1 solution. A level 2 solution would be coming up with some sort of carburation, efficient way of atomizing that particular fuel.
If I can put this in terms of Taguchi methods or robust design, it sounds to me like level 1 is parameter design and level 2 is, I can't think of the word. I suddenly drew a blank. The next step.
Tolerance design?
Tolerance design.
Okay. I don't know if I'd make that analogy yet. I'll let Shen comment on that, in May. Level 2 is parameter design?
Okay.
Within the concept.
Oh, okay.
Optimize it.
Do you have your mic on?
Oh,
No. Would you repeat that with the mic on?
Yeah, I think level 2 is the parameter design. That is the optimization within the concept, within the paradigm.
Okay.
Oh, okay, good.
Yeah.
Thank you.
Welcome.
I'm sorry to wake you like that. Teasing.
Okay, let's go on to level 3. A level 3 is an inventive solution, and by definition, any solution that is inventive essentially says there's no compromise. Now, we'll understand better what we're talking about compromise when we talk about conflicts or contradictions.
Is it really possible not to have engineering compromises?
Yeah, it really is. I mean, we don't see them too often, but there are ways of having no engineering compromises. That means you have an inventive problem when you have a conflict. An inventive solution means no compromise. The differentiator in a level 3, it is an in paradigm. In other words, this would be a fuel injection or turbocharging, you know, if we're still sort of using the same analogy. All right, it's an in paradigm solution. We could have hundreds or thousands of prototypes that would be built, and the solution typically is beyond the scope of any one engineering discipline. You've got to have cross-functional engineering teams to be able to come up with a level 3 system advancement. And it's the approach that was primarily used by Thomas Edison and his group of inventors. Now, a level 4 is a significant invention that is outside of the paradigm. In other words, here we'd be propelling the vehicle not by internal gas combustion, but by electricity, or by cold nuclear fusion, or by some hybrid methodologies. But it would be a total invention outside of the paradigm, again with no compromises. And to get to a level 4, you may have years, if not decades, of effort that would be required. And the solution incorporates many effects from physics, chemistry, and the geometrical domains, and we'll be talking about these in a little bit. So a very, very significant advancement in the system. And then level 5 is a new phenomena. It's a heretofore undiscovered physical phenomena. They spur the birth of entire new industries, for example, like a laser, a transistor, or an X-ray, or electrostatic copying. All of these things were heretofore unknown and have been, you know, truly phenomenal. Happens once in a lifetime. So the 40,000 patents were then binned or categorized
1 through 5.
1 through 5, right? Now, those 40,000 patents, this is the distribution of the 40,000 patents. 32% of them were level 1, okay? 45% level 2, and then the numbers get smaller, as we would expect. 18% were level 3, 4% were level 4, and only 1% were discoveries of new phenomena. And these percentages have remained relatively constant. Okay. Now, TIPS or TRIZ is aimed at generating level 3 and level 4 solutions. Remember, level 3 and level 4 solutions have embedded conflicts that typically we might compromise, but a level 3 or level 4 solution, whether it's in paradigm or out of the paradigm, means no compromises. It's an inventive solution, and that's why it's called the theory of inventive problem solving. Okay? Now, it also generates level 2 solutions, but it is aimed at generating level 3 and level 4 solutions.
I gather that even TIPS is not sufficiently breakthrough enough to generate level 5 solutions.
Very rarely. You have to be a mental genius like yourself to be able to...
I'm certainly glad you recognize that.
All right. So how do we solve problems with TRIZ or TIPS? First of all, the problem is formatted in a very standard format and then modeled. In other words, you know, the Russians say, make a picture, make a picture. And pictures tell a lot, and so we make lots of pictures when we do TRIZ. It is translated into a standard problem. If I were to go to the doctor and I was wheezing and coughing, the doctor would ask me, what's your problem? And I'd tell him, and he'd ask for some symptoms, and he would then translate my symptoms into a standard problem. What do you say? You have a respiratory problem, right? And for that respiratory problem, there are a number of standard solutions, right? And then from those solutions, he would pick one that would be appropriate for me. Well, TRIZ works the same way. The standard problem has several standard solutions. The standard solutions are examined by analogic analysis. A solution is found. In other words, what we're going to do is through TRIZ, we're going to model this problem, and then we're going to look at the database and say, for this model of problem, how have the other 1.5 million inventors solved this problem, or the ones that solved a similar problem to this one?
And that's an effective way of doing it, huh?
Well,
by analogy.
You look at examples. It gets you out of psychological inertia, because if I'm a mechanical engineer, I'm going to look for a mechanical solution. The solution may be in fluidics, it may be in hydraulics, it may be in electronics, it may be in composite or material sciences, it may be some other place that I'm not familiar with. And TRIZ doesn't care. It's going to say, given the problem that you have, these are the rules that apply to solve that problem, irrespective of your domain of intelligence. Okay. Okay? So that's why it gets us outside of the proverbial 9 dots, so to speak. Okay, so we analyze potential solutions by analogy. And so this is just a block diagram. We take the current problem and then we translate that in a standard problem. We then look at the database. The database contains standard solutions. We look at analogies, and then we come up with our solution.
Let me ask you a question. This is not something we've discussed. With regard to the TRIZ database, which I understand is expanding and continues to expand, can we anticipate that with the supplemental information provided by the expanded database, that in years to come that TRIZ might be expected to be even more powerful than it is today?
Yes, it grows all the time. You have not only new technologies and examples and physical and chemical effects that are being added to it, but new applications into not only engineering realms, but other realms, management practices.
For example, yeah.
Yeah, I mean, many of the laws, if you will, or regularities or patterns of behavior or solutions are the same for an engineering problem as they are for a management problem. We're going to be talking about, we're going to be talking about things like separation principles, separating a conflict in time or space. Well, I have done that when I have run into management problems. I have separated them using TRIZ principles. So there's been an application of TRIZ not only in engineering, but areas of safety, areas of biology, areas of science, areas of management.
So could you even resolve, for example, a union management disagreement?
It's possible to formulate that problem into a series of contradictions and then looking at how those contradictions can be broken up and or resolved or separated using inventive principles, which we'll talk about.
Fantastic. Okay, good stuff.
All right. So one of the fundamental principles that came out of the study of the 40,000 patents now is the fact that we run into these conflicts or contradictions. That creates the inventive situation, right? So we've got three contradictions that we're going to be talking about. Administrative contradictions, technical contradictions, and then physical contradictions. So TRIZ is essentially an outgrowth of dealing with conflicts or contradictions. The other thing that is a sort of a founding principle, if you will, of TRIZ is the thought of ideality. And ideality is simply the ratio of useful versus harmful function that's performed by a system. Now, what would that sound like to you?
That sure sounds to me an awful lot like Dr. Taguchi's signal-to-noise ratio.
Absolutely. Okay, so it's really interesting that at parallel times in two different countries, the same thought of signal-to-noise and ideality appeared, and essentially it's the same formula. One was applied at a macro sense, at a system level, and the other one was applied at a parameter level.
Right.
Okay? And I find that, you know, absolutely utterly amazing. All right, so we have ideality, and what gives rise to ideality is these the laws of the evolution of technical systems. Now, these aren't real laws. These are more patterns or regularities of how systems evolve over a period of time, and we'll talk about those a little later. All right, so let's talk about contradictions or conflicts. So first of all, I define it as the direct opposition between things. And, you know, when I first got my computer, that's what I felt like doing with it. It was a contradiction. Most oftentimes, what do we do with them, Jack, when we're confronted with these things?
We try to ignore them.
Yeah. We try and sidestep them. We try and skirt them. You know, we avoid these things. And typical solution, if we have to deal with a conflict, is we're going to make a compromise. I want horsepower and I want fuel economy. Well, I can't give you both.
And I want it now.
And I want it now, but I'll give you a little of both, but I can't give you all of it. Now, these contradictions then will provide the basis for inventive solutions. When we have conflicts, and we always do, then we need invention. Okay. All right, so let's talk about administrative conflicts. Administrative conflict simply is the initial definition of the situation that has all the other embedded difficulties and or contradictions, okay? And it defines the desirable but elusive condition. For example, administrative conflict would be, we need to accomplish something, X, blank, X, whatever that is, but we don't have a clue as to how to do it. Okay, so we got a problem, we don't know how to solve the problem. Administrative conflict, okay, so that sets the stage. Now, a technical contradiction or a conflict. That's when several elements or parameters of a system are in conflict. And we see that all the time. And what makes it a contradiction is as one parameter is improved, the other one is made worse. So it is one at the expense of the others, A versus B. Okay, our typical reaction is to trade off, right? To make a compromise. Okay.
These are the kinds of things that show up in the roof of the House of Quality.
Absolutely.
The A3 matrix, depending on your orientation.
Right. Absolutely. Now, systems may have numerous embedded technical contradictions, and oftentimes they do. Lots of embedded technical conflicts in systems. Here's an example: power versus fuel consumption. I mean, that's one that we can all relate to.
Oh, yeah.
You know, so that would be, as we want more horsepower, our fuel consumption is going to get worse. Okay, so one parameter versus the other parameter. All right, now, a physical contradiction. Characteristically, a physical contradiction is one controlling parameter between two technical contradictions.
It almost sounds like an impossibility.
Yeah, it sounds dichotomous, but it is a controlling parameter that must be in two self-opposing states. In other words, it's got to be big, it's got to be small, it's got to be hot, it's got to be cold, it's got to be there, it's got to be not there, okay?
Simultaneously or at different points?
Simultaneously. Simultaneously. It's got to be in two different simultaneous states, and we'll give you an example that should explain it. Now, as I said, if we have a technical contradiction, oftentimes we will find a controlling parameter between those two technical contradictions, and if we can find that controlling parameter, that would be the physical contradiction. Now, solving problems involving physical contradictions provides more elegant solutions, and that's what we want to do. If at all possible, we want to look at the parameters that are fighting each other, horsepower versus fuel, and then find out is there one controlling parameter between the two of them, and then use the solutions from TRIZ for physical contradiction. Sorry. Okay, now here's an example of a physical contradiction. Let's say that I want to machine something. I want to turn a piece of steel. My boss...
For the non-metal workers in the audience, what do you mean by turn a piece of steel?
With a cutter, I want to take a cut across that piece of steel.
Okay, and remove some layer of the metal.
Remove some layer of the metal, absolutely. So my boss wants high productivity, all right? But we also want very high surface finish, do we not?
High surface finish meaning very smooth.
Very smooth, okay. Now, if, however, we run that tool very quickly across that piece of steel, we're going to have high productivity, but actually what's going to happen? We're going to have low or poor surface finish.
Okay. It sounds like me shaving in the morning.
Right. So that would be a technical contradiction.
Mm-hmm.
Right. You want smooth shave, but you want no cuts.
Right.
Okay.
And I want to do it as quickly as possible.
As quickly as possible, right. Now, the physical contradiction would be the metal removal rate. That's the one controlling parameter.
Mm-hmm.
Okay. Because metal removal rate has got to be high for productivity, and it's got to be low for surface finish. In other words, it's got to be in two self-opposing states.
At the same time.
At the same time, right?
And you're going to show me how this can be done.
So, if we can solve the problem of metal removal rate,
Yeah.
okay, then by definition, if we can separate that conflict, then we ought to be able to handle the technical contradiction.
That would follow.
Right.
Okay.
I mean, the logic follows, right? Okay. So, solving problems with contradictions. Administrative conflicts reveal the technical contradictions. We want to do something, but we don't know how to do it, right? We don't have a clue. If there is an embedded physical contradiction, the most elegant solution is at that physical contradiction level. In the absence of a physical contradiction, a solution between technical contradictions is possible, albeit less elegant. Okay, but it's still possible.
Okay, am I seeing a hierarchy now?
Yes.
From administrative to technical to physical contradictions?
Absolutely, absolutely. And our strategy, you know, that comes out of this, you know, Altshuler's research showed that technical contradictions were solved through similar strategies. So in looking at the patents, given the fact that that problem had been abstracted into a technical contradiction, the same solutions appeared at different points in time by different inventors in different countries. Okay? And this gave rise to the whole theory there's a construct at work here. All right, so the solutions that were found were abstracted into the 40 inventive principles, or 40 principles for solving that particular conflict or contradiction. And to be able to map the problem to the inventive principle, Altshuler devised a table of engineering parameters that had 39 engineering parameters and put them in an L-type matrix so that you could say what are the engineering parameters that are in conflict, and then what are the inventive principles that have been used to solve this particular conflict. Okay?
I'm with you.
All right? So here's an example of some of the parameters. There are 39 of them. I didn't list all of them, but just some of them, you know, like weight of the moving object and so on and so forth. So those are some of the parameters.
Could you just give us pick any one of them and discuss it very briefly for us?
Well, temperature. Things
Okay.
are hot or cold.
Okay.
Or strength, you know, how strong an object is, and if the strength of the object had to be reduced, for example, and if the strength of the object were going to be reduced, that might in some way impact weight of the moving object, or weight of the moving object might impact strength or something like that. These are typical engineering parameters.
Okay, so power would be a high power versus low power.
Could be, yes.
Okay.
Yeah, changing the parameter for power.
Like takeoff versus landing?
Right. Or takeoff versus cruise.
Cruise, yeah.
Okay, something like that. All right, so here's a very small portion of that L-type matrix with some of the engineering parameters. I've just listed 3 of them: speed, force, and power. And then see the numbers within the matrix there. Those numbers then are the inventive principles, which I'll show you next, that have solved that problem that have been contained within the database of patents. Now, the order that you solve them in is as they're listed. For example, if I have a conflict between force and speed, then inventive principle 18, 29, 15, and 12 in that sequence are the preferred solution pathways.
Okay. I was just doing a check of this versus the previous graph that we were looking at. Number 13 shows up on there twice. 35 shows up several times.
Okay, yeah,
but they're not on here. Okay.
yeah, wait a second. You're looking at the parameters here, Jack. What we have, the
You're
numbers
right,
in there
you're right.
are the inventive principles. So let's
Right.
get to the inventive principles. These are the 40 inventive principles. For example, like the principle of segmentation or fragmentation. Take something and fragment it. Asymmetry. If something is not if something is symmetrical, make it asymmetrical or increase the degree of asymmetry. Okay, that's the principle of asymmetry. Prior action. I'll give you a cute example given to high school students. If you had to have a cast on your arm and you had to take that cast off by yourself and you couldn't cut the cast from the outside, how might you be able to remove a cast after it had been on for 6 weeks? Okay, well, the principle of prior action solved that problem, and in essence the solution was to put a hacksaw blade pointing out inside the cast so that you could saw your way out.
Like putting a file in a cake to get you out of the prison.
Right, exactly.
Okay. On that light note, we've only got about a minute left, folks, before we take our break. We still haven't heard from any of you with regard to any questions. I personally find this material fascinating. I would hope that you do. If during the break you choose to give us a call or give us a fax, we'd be happy to hear from you. But for goodness sakes, don't forget that we're here. This is a live telecast. This is a very expensive consultant we have here, and a very bright guy to boot. And here you got a chance to get him just to yourself and ask him some really important questions. So don't hesitate to call or fax in your questions. Steve, we're about halfway through our telecast. We've got about 80 visuals that we're using, and we're just about to the middle of this right now. Let's just say see you soon to our audience, and we'll talk to you in about 10 minutes. Take your break, write your questions, call your questions in, and we'll see you in about 10 minutes. Take care. Well, here we are back again. I hope you made the best of your break. I was just noticing on the visual that comes up just before we come on the air, you'll notice it said 1 of 5. That doesn't refer to this telecast with Steve. There's not 5 more telecasts with Steve, although I'd love to have that opportunity. This is the first of 5 in the series, the first half of 1995, on Continuous Improvement TV, CITV. And so that's what we're making reference to with 1 of 5. Next month with number 2, we'll have Peter Schultes, as I mentioned earlier, number 3 with Bill Conway, number 4 with Shin Taguchi, who's here in the studio with us today, and number 5 with George Box in June of this year. Please give us your calls. Let us know if, Shin, you were just on camera. You didn't know that. And God, you lost me there. Okay, we had a call. Let me tell you, we had a call during the break from a gentleman named Dan Phelps. And Dan is watching us from Eastman Kodak. And Dan had 2 questions for Steve. I'll act as the sit-in for Dan and repeat his questions for you. First, Dan wanted to know from Steve, with regard to the electronics, computers, and chemical industries, are there any TRIZ applications that already exist that Steve could comment on? And second, is there any particular place that Steve could recommend where information on TRIZ could be obtained. And so, Buddy, I'll ask you, first of all, can you comment on any applications of TRIZ in the area of electronics, computers, and chemistry? And then where can Dan and his associates at Eastman Kodak pick up additional information about TRIZ?
Yes. The first question on the TRIZ in electronics, it's applicable in electronics like in any engineering discipline. The number of cases if TRIZ applied in electronics is smaller as compared to mechanical engineering, obviously because of the fact that electronics is newer on the scene.
Sure.
But the principles and laws that apply in electronics, whether you're making microprocessors or EEPROM chips or what have you, and you can use them in electronics, chemical engineering, same kind of thing. So this is a set of generic laws, principles that we use irrespective of the particular engineering discipline.
Okay, the physical aspects of it.
The number of analogies or analogous examples that we can take a look at are less in electronics because it's just going to take some time to apply it in that area. But there are some there that are already there.
Would it be safe to say that they're proportional to the history of that particular function?
Absolutely, right.
Okay.
Yeah.
So, for example, physical type things like in civil engineering.
Construction, all those kinds. There's tons of examples.
Okay.
Tons of examples.
Okay, so Dan, hopefully that helps a little bit with respect to the fact that there are examples of TRIZ applications in each of the three areas, as well as a number of other areas that you asked about. Now, how about where can folks find additional information about TRIZ?
Well, obviously, we at ASI have information on it, and whether it's solving problems using TRIZ or software or what have you, and so our telephone number is area code 313-336-8877.
Isn't that on the very last visual of our...
It's also on the last visual. So.
Yeah, so if you folks take a look at the visuals you have, page 79 of your visual, you can contact Steve or anybody at ASI. Just tell them you want more information about TRIZ, and I'll repeat the number that Steve just mentioned a moment ago, area code 313, which is the Detroit, Michigan area. Phone number is 336-8877. And if anyone else has any calls, comments, questions, faxes, we'll be here for about another 50 minutes or so, and we'll look forward to hearing from you. And now back to page 39.
Okay, so we had ended up with the inventive principles, and there's the 40 of them. Again, now, so we want to map these back to where we came from. So the 39 engineering parameters are the ones that are in conflict, and the intersection of those engineering parameters with those numbers that were embedded at the intersection of those two engineering parameters would be one of these inventive principles, okay, that had been used previously by inventors to solve a problem. And while these are just one-word descriptors here, there's a whole list of examples of how, for example, prior action or nesting or combining or asymmetry or copying or what have you has been used in the past.
Okay.
Okay? All right. So that's solving technical contradictions. Remember, parameter A fighting parameter B. Now, let's talk about physical contradictions. They pose the greatest challenge and the possibility for the most elegant solution. Isn't that right? It's a risk-reward kind of a situation. Physical contradictions are solved through separation principles. We can separate things in time, space, or we can separate things in scale. We can separate things between the component and the whole, and we'll give you examples of all of those.
Okay.
All right? So, first of all, separation in time. First of all, that says that a parameter or an element of the system is present or absent at different points in time. And the example that we have here is the landing gear on an airplane. Well, when do I need the landing gear?
When you're on the ground.
At takeoff and landing, right?
Yeah, and when you're trying to roll around the runway.
Absolutely, absolutely. Now, once I'm in the air, I don't need the landing gear. So the physical contradiction is that the landing gear must be there and it must not be there, right? So how can I separate that conflict? In time. It's there when I need it. It's not there when I don't need it. Same thing with flaps or sweep wing geometry. If I'm sitting on the deck of a carrier and I need to take off, I need large wings for maximum lift.
Right. Oh,
okay.
oh, right.
Right. I need large wings for maximum lift. Once I'm at altitude, I need small wings for maximum maneuverability. Right. So the physical contradiction on the wings is they must be large and small. So through sweep wing geometry, we separate the physical contradiction in time.
Gotcha.
Okay?
Steve, we have Dan Phelps from Kodak.
Okay, folks, I don't know if you heard, Dan Phelps is back on the line with us from Kodak. Go ahead, Dan. Let's hear what you got to say.
I have heard some about the TRIZ principles before, and I understand what you've been talking about in the presentation. However, I'd also heard several comments that said these sorts of principles have been applied to look at patent portfolios for various companies. And I was wondering if you would care to comment on whether or not that really has happened, and if so, where one might be able to get some information about how people have done it.
Okay, thank you, Dan. You want to repeat that and then respond to it?
Dan asked a question that he understands the principles, and he knows that they've been used to examine patent portfolios of companies, and where might he get more information. Dan, is that essentially your question?
Yes, I'm assuming that they really have been used for this analysis. I mean, you read things and people refer to it, but I've never seen an actual example.
Okay. I know of a number of instances where companies have called in TRIZ specialists, and they have gone to the patent libraries and searched all the patents for that particular product that they're trying to make an improvement in, and then from that patent search have traced where they are in the evolution of that particular product. Now, we're sort of getting ahead of ourselves a little bit in answering this question right now, because we're going to talk about the evolution of technical systems. But yes, in essence, you can look back in time at the patents, apply them through the laws of invention, and then map where you're at on the life cycle curve, and then predict future derivatives of your product. So I know a couple of instances, companies that I'm familiar with and people that I'm familiar with. I'm not at liberty to say who they are, but that has happened. It is probably ongoing now. There may be, your competitors may be doing something like that. You know, so that is a part of TRIZ. I mean, you can look back, you can then predict future derivatives.
I think it might be safe to say, let me add and make sure I'm correct on this, that by doing this kind of research, you can tell where you are on the life cycle, and if in fact you can expect to see, you know, a third step, a fourth step, or you may already have achieved, you may already be in that mature state, and should not expect a change,
breakthrough.
a breakthrough. You literally have to go to a level 5 kind of.
You need some phenomena, some new physical phenomena that needs to be discovered that may change the paradigm of your particular product. Okay, but
like back in the 50s, at the time that xerography became popular, when Haloid became Xerox, the most popular method of copying materials was using 3M's Thermofax, and before that the Ditto machine, and each one of these was a step function, a level 5 change from the way it was previously done. And you know, if I understand correctly what we've been talking about, by evaluating the history of a particular product, you can tell whether or not, you know, you're going to need a level 4 or a level 5 breakthrough to achieve continued success, or if in fact a level 1 or a level 2 could be expected next.
Similar. I would say you're pretty close. You would know what's going to happen. You would have a high probability, I should say, let's be more accurate, more precise, a high probability of understanding what the future derivative of that product is going to look like, what it's going to change to, if you understand the laws. And so it's a matter of mapping, finding out where you're at, and then looking at what the future scenarios are likely to be.
Okay, for example,
thank you very much.
Go ahead, Dan.
I just said thank you very much. I'll let you get back to your regular presentation.
Thank you very much. I appreciate your calling. Anybody else has any thoughts on that? Please give us a call. Let's run with it.
Okay, we're going to have to maybe speed up a little bit. Okay, so contradiction, separation in time. Here is separation in space is another way that we can separate a physical contradiction. So separation in space is a parameter element of the system is present or absent in some sort of spatial orientation. And here we have a funnel, that's an example. It's wide and it's thin. My bifocal lenses are thick and thin. A funnel, all these things are examples of separating things in space. Separation scale, a parameter is large or small in relation to the medium it operates in. For example, any kind of a filter, a coffee filter, I was thinking about this as we were talking, you know, it's small relative to the coffee beans and the grind, but it's large relative to the water. It lets the water to drip through. Inline filters, a kitchen sieve, a colander, it's small or large depending upon the medium that it's operating in.
Gotcha.
Okay. Separation between the parts and the whole. A parameter element exhibits opposite characteristics in comparison to each other. We're talking about the system versus the components. For example, a bicycle chain is flexible, right? But at the opposite of the extreme, each link at the component level
Very rigid.
is very rigid. Absolutely right. So that's separation between the parts and the whole. All right, now the solution pathway to solving problems. We're going to define the administrative conflict. We've got a problem, we don't know how to solve it, and then from that we're going to reveal what the technical contradictions are. If we can go and find a physical contradiction that controls the two or more technical contradictions, then we're going to use the separation principles that we've just talked about, Jack, to solve that problem.
Right.
If a physical contradiction does not exist or we can't find it, you know, we don't know where it is or what it is, then we're going to use that parameter table that we had talked about and the inventive principles, and that's going to lead us to a solution.
So the TRIZ is not that rigid. The flexibility it provides is that if a certain path is not capable of leading you in the direction you need to go, there's an alternative methodology.
Yeah, you reiterate, reformulate the problem,
Gotcha.
look elsewhere.
Okay.
All right, so those are contradictions. Remember, that's one of the fundamental building blocks of TRIZ. Another one is ideality. All right, now ideality is a definition, the definition I have is a standard of perfection, excellence, and ultimate object. You know, it's the ideal final result. And the formula, I there, equals sum of useful function over sum of harmful function. And again, we said that this is...
That looks very familiar.
Okay, signal to noise ratio.
That's it.
It's exactly the same thing as signal to noise ratio. So if you want to pick off the right parameters in your product, you pick the ones with high signal to noise ratio or high ideality, right?
I like signal noise ratio better.
Okay. All right, now ideality. It says in a macro, at a macro level, technical systems evolve to higher levels of ideality, and this movement is inexorable, traceable, and predictable, and that's essentially the conversation that we've had with Dan at Kodak. And understanding these laws now provides clues to solving difficult problems. Okay?
Are these really objective laws?
They're not really objective laws. They're more like high probability patterns.
Okay.
Okay, and but you know, as we're getting the syntax right with what the Russians call laws, we would say, well, that's not really a law the way we describe a law. It's more likely a pattern or a probability that's going to occur. It's a very high probability pattern.
Okay. Well, you know, in Russia, their laws are very different from American laws.
Granted, yes. All right, so let's go through these laws now, Jack,
Okay.
all right? First of all, a product emerges, and that's when two things happen in time. There's a need, and some functional ability to meet that need is present in the marketplace or technologically, okay? And so a product emerges. What happens after that is it starts to increase in ideality, or the signal to noise of the product gets better over a period of time. You have increased usage of resources. Now, we're going to talk a little bit more about what resources are. Resources are those elements or substances that are in the system that can be utilized to more effectively, to make the system more effective. Okay, the resources. Some of the contradictions could be eliminated, and we get more functionality. So we get increases in ideality. All right, systems as they start to mature, as they start to develop. The other thing that happens then is we have an uneven development of subsystems. In other words, there's a differential rate at which subsystems evolve. So some subsystems are ahead of others technologically. I may have a great engine but a lousy powertrain, or I may have a great chassis but lousy suspension. I have a differential between the rates at which various subsystems evolve. The factors that create this uneven development of subsystems are the unresolved technical or physical contradictions that are still embedded in the product, psychological inertia. We don't want to admit the fact, and maybe we just don't have the enabling technology. So the message here, however, is when we have uneven development of subsystems, we get dissonance in the entire system.
Okay.
All right. And so, as engineers, what do we try and do? We try and reduce the amount of dissonance that we have in a system. All right, next law, dynamicity.
I admire your pronunciation. I couldn't say that.
Essentially, it says that these systems become more dynamic with time. For example, they could become more multifunctional. You know, this is the Ronco, it slices, dices, it does everything. There's more function there that systems will provide over time. Or another way that systems become more dynamic is you have the increasing number of degrees of freedom.
Right.
For example, a hinge has 1 degree of freedom. A ball in a socket has almost unlimited degrees of freedom. So systems become more dynamic.
Right. Which is why we have a ball and socket in our shoulder as opposed to a hinge for mobility.
Yeah, very good.
Okay.
All right. Or we have changes in states of stability from non-dynamic to dynamic states. For example, an airplane on the ground is not very dynamic, but in the air, it is very dynamic. Okay, so these are the ways that systems become more dynamic. And that, again, is one of the laws. Now, by the way, I failed to mention, but these 8 patterns or laws are like the header cards of an affinity diagram. There are 200 sublines of evolution underneath these 8 major headers.
Okay.
Okay, so it's a fairly, the resolution on these laws is fairly precise.
Okay. Sounds very comprehensive.
All right, transition to bi and poly systems, then convolution. This is another law. In other words, what this says is that you will take a single system and it will become combined into a bi-system or a poly system, and then it will convolute into a super, single, or mono system. For example, if I have a pencil and I also have an eraser as 2 independent systems, if I combine the 2 of them together, a pencil with an eraser, I have a bi-system that is now convoluted into a super system.
How about a pen that has 4 or 5 different color inks in it that you can
Same
press
thing.
Okay.
Okay, that is a poly system.
Yeah.
Okay, that's an example of a poly system. The Gatling gun is an example of a poly system.
Multi-weapons strapped together effectively.
Absolutely, absolutely. A multimedia computer. All of these things that we have in a multimedia computer used to be separate independent systems hardwired together and strung together, and now we see them as convoluted into one super system. Okay? So this is another inexorable thing that's going to happen to systems. They're going to combine in strange ways with other independent systems and then convolute.
I'll give you an example of one that it's become very popular recently. That's the Pictophone, where you've got a TV screen with your telephone and you have it involved with a clock radio with an alarm.
Sure. It's a perfect example of what we're talking about here. Okay, so this is another one of the laws of evolution. Harmonization of rhythms. Remember when we talked about that subsystems evolve at different rates? What this says is that eventually what's going to happen is you're going to get to a point where the dissonance between the subsystems is reduced. Okay. In other words, the rhythms and or that system becomes fairly well optimized given the current technology that's out there, and all the systems are at about the same point of capability, if you will. All right. So when this happens, you get a state of equilibrium that is established. And we've got a little cartoon, a Far Side cartoon that sort of illustrates this. It's
this one here?
Nope.
This one?
Nope. Next one. It's this one here. If we could do a top-down shot on this.
Okay, could we get an overhead camera shot on this, folks? There we go.
Okay, if you could zoom in on that. I'm a Far Side comic fan. It says here they're playing. You know, they're doing the paper, rock, scissors, and all 3 of them have rock, and it says before paper and scissors is invented, and the guy says, dang, tied again. Ready, 1, 2, 3. And so that shows that at that particular point, those rhythms are harmonized, right? I mean, they keep doing the same thing over and over again, and there's a state of equilibrium that gets established for a period of time. Anyway, so.
This is from the best of Far Side, 1986, if you still have that calendar with you.
Yeah. All right, so. Harmonization with them. And we see this in things like bicycles. bicycles have come a long way, but we don't see tremendous amount of changes in bicycles. They're changing, but not the radical leaps that we saw 10, 15, 20 years ago. Refrigerators, power tools, and the list goes on. They've harmonized the rhythms. All right. Transition to micro levels and increased use of energy fields. The energy transformation in the system becomes shorter and more efficient over a period of time. And systems become smaller and they use energy fields. The examples that we have here is a cast iron stove versus a microwave oven. The difference in size and also use of energy fields. Or a locomotive versus magnetic levitation. Or telephones now with 1.5 watts and a small little cellular phone, you can call anywhere in the world. Okay, so using microprocessors, another example of use of energy fields and transition to micro levels.
Did you see Back to the Future 3?
Yes.
Levitation of the locomotive.
Yes, okay. That's not what I was talking about, okay. All right, the last law is increasing levels of automation. In other words, the need for human interaction is minimized. Systems become self-regulating and autonomous. For example, the automatic teller machine or an autopilot. Once I put the autopilot on the airplane, it pretty well took over. I didn't have to do much thinking other than just to monitor. Smart suspensions, smart cars, all of these things where the system itself takes on the characteristics of a human being.
Artificial intelligence, if you will.
Yes, absolutely. So those are the laws. Now, so we've talked about ideality, we've talked about contradictions, we've talked about the various parameters and ways of solving those. Now we want to get at more specifically what are some of the tools of TRIZ, of making solutions, getting at solutions. Okay, so we're going to talk about the structure, this algorithm that is a part of TRIZ called ReVelle. Again, that's a Russian acronym. Substance field analysis, or what we say is SU field analysis. Resources, we're going to talk about the various effects, physical, chemical, geometrical, and some other things like technological forecasting and subversion analysis. Okay, let's look at the structure. First of all, at the bottom, we're supporting the entire thing that's all built on what we saw in the inventive solutions contained within the database of patents. Those patents gave rise to the laws of the evolution of technical systems. Okay, from those laws, we extract out the algorithm, the ReVelle algorithm that we're going to talk about, and the system of standard solutions, which is the SU field analysis. Okay, so the laws support those two things, and between ReVelle and SU field, or system of standard solutions, there's a lot of iteration. That's why there's a double-headed arrow that goes back. You formulate a problem, reformulate it, look for a solution. Again, change your formulation if you don't get a decent solution. So there's a lot of iteration. And then, again, impacting all of those are physical, chemical, and geometrical effects. So a high-level block diagram as to what the structure of TRIZ is. So let's talk about ReVelle. ReVelle is a non-computational algorithm that systematically analyzes a problem and it reveals a contradiction. A problem well described is half solved, and that's the objective of the ReVelle algorithm, is to get you to search for what is the problem that you're trying to solve. And so in the ReVelle algorithm, you not only model the problem, but you model where the conflict zone of the problem is, where the conflict time of the problem is, and it's a very, very rigorous way of describing a problem.
I'm really surprised that it's non-computational. It would almost seem to me that something as technically oriented as this would be basically computational in nature. But so I guess this part surprises me.
It's logic. It's a decision tree. It takes you through a series of decision gates as to what the situation is, and then where in TRIZ you need to use the laws, and which laws you need to use. It'd be, if I can give you an analogy, it'd be like if your competitor had some tremendous technology that they had discovered, and all of a sudden they were really impacting in the marketplace. And your boss told you, I want you to go to the library, to the McGraw-Hill Encyclopedia of Science and Technology. It's a 20-volume set, and I want you to search each page to find out potentially which technology did they incorporate into the product to solve that problem. And you went there dutifully and you turned every page in all 20 volumes. What are the chances that you'd find the right technical solution for your problem?
Slim to none.
Slim to none. Okay, now, on the other hand, if your boss said, I want you to go to the library and get the McGraw-Hill Encyclopedia of Science and Technology and look at these 4 pages, okay, and figure out from these 4 pages which technology to use, would you likely have a higher probability of solving the problem?
Extremely high.
Okay. That's what the ReVelle algorithm is, non-computational, but it searches you or takes you through a series of decision gates to get you to the 4 pages.
So it's like a funnel. You start out with, with all 20 volumes, and it gets you down to 4 pages.
Down to the 4 pages. Exactly right. Exactly right. It overcomes psychological inertia, rounding up the usual suspects. That's from the movie Casablanca. Whenever we have problems, it seems like what we end up doing is sort of rounding up the usual suspects, and it stimulates a creative process, and it moves us toward ideality.
Gotcha.
All right, that's the purpose. So the steps within a ReVelle, you describe the situation, and then you state the so-called, what is called the mini problem, and that is the technical contradiction that you're trying to solve. Okay, you start stating that problem. Then you model the problem, as the Russians say. You make a picture. When you make a picture, you also ask for this thing called X element. An X element is a potential solution within your system that would solve all your problems. And like we did in algebra, we solve for X. So X element is that magical thing that if it were present, it would solve all of our problems. And so we say, what does X element have to do to solve this problem?
That's very similar to what Dorian Cheney calls the big red X.
Right. Okay. Then we diagram the conflict, and we get more detail on what the conflict looks like, and we identify the conflict zone and the conflict time. Is it T1 before the event, T2 during the event, or T3 after the event?
Gotcha.
When is the conflict time? Then ReVelle asks us to identify the available resources. What is in the system that we can use? Is there heat there? Is there space there? Is there some movement? Is there something dynamic that we can use in the system to solve the problem?
That's already there.
That's already there. Is there a resource that's available? Because if we use a system resource that comes along for free,
it costs us nothing extra.
It costs us nothing. You got it. Exactly right. All right. Then the other thing that ReVelle says, define the ideal final result. In other words, if you had absolutely
no constraints,
what would the ideal solution look like? And this gets us out of psychological inertia.
This is the as-is versus should-be gap analysis.
That's right. That's right. So what is the ideal final result? And then in that whole process, again, you start revealing, well, what prevents us from getting to the ideal final result? You say, well, this would be the ideal result, yeah, but I can't get there because, and all those becauses then become the technical and physical contradictions that we use to solve the problem. And that's where we're going to apply the system of standard solutions, or Sue-field analysis. The problem, if we don't like the problem, then we reformulate the problem, either at a higher system level or at a component level. I mean, so we keep reformulating. So that's essentially the ReVelle algorithm. Okay, let's talk about this thing called substance field analysis.
Could I just ask one question? That last one we were just looking at on 59, could I get the overhead for a second so we can hit this number 59? It sounds to me, like with the experience you and I have both had with problem solving over the years, like this sounds a lot to me like Kepner-Trago. Is it?
It's similar to Kepner-Trago. In Kepner-Trago, they ask you, when is it not, what is it not, and all those kind of things. And so in defining the conflict zone and the conflict time, there's some elements that are similar to Kepner-Trago as part of the treatment.
It sounded familiar.
Yeah.
Okay.
Yeah.
Okay, let's go back on then.
Okay, so we're on substance field analysis. We're on slide 60. In substance field analysis, essentially what we do is we start diagramming what the system is that we have, and we have some standard designations, but a system, in order for it to be a system, must contain two substances, two things in some sort of field. For example,
at least two.
At least two. And there could be more, and there could be more than one field, but it must contain at least two substances in a field. For example, this mouse, the ball underneath the mouse there, that and the pad here are two substances, right? And there is a frictional or mechanical field between the two of them. So S1 would be the ball, S2 would be the pad here, and then friction would be the field or force that connects them and makes the mouse a mouse.
Yeah.
You know, other than that, I don't have a mouse. If I just have no friction, there's nothing I can do, right?
You've got a non-functional device.
That's right. Okay, so the first thing that we have to do is to complete the SU field.
Gotcha.
And we'll get to that in a second. So the advantage of using SU field analysis, the engineering system is depicted in a standard structural format. The reason this is an advantage is, again, it gets us away from psychological inertia. When we use our current drawings and prints, we tend to then get trapped by our own psychological inertia in looking for solutions. It's just like in algebra. We use A plus B plus C, right? We use abstract terminology in order to solve a problem. And we're using a standard structural format in TRIZ to be able to depict what does a system look like? What are the substances? What are the fields? Okay?
Okay.
Because there's a standard solution for a certain format. All right. So it provides an objective basis to initiate the search for solutions. And these solutions have been derived from the patent database, and there are 76 standard SU field solutions. Okay, now we won't be able to look at all of them, obviously, but I'll show you a couple of them. Okay, some of the designations. S1 is the tool, S2 is the article. Okay, the tool works on the article. The interaction is from the tool to the article. All right. F is a field, and while there are a number of them, the ones that are most popularly used are mechanical, electrical, magnetic, thermal, or chemical field. You know, something that binds a system together. The transfer of energy, it's got to be through one of these fields, right?
I'm thinking back to Dan's question a little while ago. Two of the three fields he was talking about are on there, but he also mentioned about computer field. Is that another field that we could include?
Well, but computers use electronics, right?
Ah, so it's classified under the electrical.
Right.
Okay.
Okay. And you know, and if you listen to Shin Taguchi, he'll say, you know, in order to solve a problem at a parametric level, we need to understand what the energy is in a system. What is a field or the flow of energy in a system? So we don't have a system unless we have a field and a couple substances connected by a field. All right, now the designations. We've got a useful effect. I'm just going to grab this pencil over here. So the useful effect is a solid line. An insufficient effect is a dashed line. So between the tool and the article, the effect is not strong enough. If it's harmful, then we're using these asterisks here. And then the solution operator, this is the solving of the problem, okay, is a double line with an arrow on it. So useful, insufficient, harmful, and then the operator or the solution to the problem. It's not a person, it's a solution to the problem. Okay. Now, we're going to go over some of the rules. One of the rules of SU field analysis, if a problem contains an incomplete SU field, then to solve it, first of all, you've got to complete the SU field triangle. In other words, if you have S1 and S2 only, that's this situation, right? Okay, where the mouse is above the pad, I don't have a field, I don't have two substances in contact, or S1 and F2 only, or S2 and F1 only, then in order to solve a problem, I've got to introduce either another substance or a field.
With you.
Okay, and the example that I give here, that if I want to increase the rate at which solids separate, I have to use something like a centrifuge. So I have solids in a liquid, and they won't separate unless I put a gravitational field on them and spin them, and then I get separation.
Gotcha.
Okay. So first of all, rule number one is complete the SU field triangle. All right, rule number two. If a SU field is complete but problematic, the system can be improved with the introduction of a third substance, S3, which is a modification of S1 or S2. So, if the example that I give you, if we have wet coal on a conveyor that's being conveyed on a conveyor and it is sticking to the conveyor, okay, we can prevent that by mixing in coal dust. So let's just explain. S1 is the coal, S2 is the conveyor, and there is a harmful interaction between the two of them that is caused by mechanical forces, right? They stick to each other. All right. The solution operator says that if we introduce a derivative of either S1 or S2, now we can't introduce a derivative of S2, that's a conveyor. But we can introduce a derivative of S1, the coal, and put in some coal powder, for example, to absorb the moisture. And so S3 then intersects the harmful interaction between S1 and S2, and it prevents the coal from sticking to the conveyor. Okay?
I'm with you.
All right, so that's a standard system transformation. So whenever we model a problem in a ReVelle, and this is the model that we have, the first solution we ought to look for then would be this solution. Now there are some others, but this would be the first one we'd look for.
Okay.
All right. The third rule, if there's a harmful effect between S1 and S2, another field, F2, can counteract the initial F1 field. Okay, the example I give, in machining, heat is generated by metal cutting and is removed by coolant. So, S1 is the tool, that's the carbide-tipped cutter. S2 is the piece of metal. There's a mechanical force between them that is creating the cutting action, and it's harmful. All right, so what I can do is I can intersect that harmful interaction with a thermal field. I can put coolant on it, right? It's a different field that counteracts the harmful field that I have between S1 and S2. Okay, so that's another example. Another rule of Suffield, if the effect between S1 and S2 is insufficient, replace it with S3 and F2. And the example that I give you is using heat to remove paint. So in the example above, S1 would be a scraper, S2 would be the paint on the wall, and the interaction between the two of them is insufficient. I can't scrape all the paint off the wall. There's a mechanical force between the two of them. So the solution operator says that what you ought to do is substitute S3, a heat gun, and a different field, a thermal field, to have the paint come off, right? And aren't you doing something like this at
yeah.
X bar and R?
Yeah, for those of you who've watched this show previously know I live a good deal of the time now in Tucson, Arizona, where we've purchased a home 40 acres south and east of Tucson called the X Bar and R Ranch. And we're trying to fix the place up a little bit, and we've just expanded the bathroom by about 50%, and in so doing we had to eliminate some tiles that were on the floor outside the original bathroom. And the gentleman who's helping me do this work was trying to scrape off the tiles from the floor, and he was not able to do it mechanically, so we introduced a little propane bottle with a flame, and what he would do is heat the tiles and then try to use the scraper. The problem we ran into was that by the time he put the bottle down and got the scraper up and started to scrape, the tiles had cooled off too much, and so he brought me into it as the third force, if you will. Or am I a substance? I'm not sure. At any rate,
You're a phenomenon, right?
at any rate, so what he would do is he would take the propane bottle, heat up the tiles, I would use the scraper, and it came off, and we had the whole thing done in under 5 minutes. But yeah, this is very, very accurate portrayal of that particular situation.
Yeah, exactly the same Suffield structure that you had with those tiles is what's represented here up above, and then your solution was exactly the same. All right.
I'm a TRIZ example right here. Living example.
Living example. Now, the thing about using this structure and then using Suffield transformations is that, again, it gets us outside of psychological inertia. I can give people a similar problem to like the one up above, and they will come up with a different answer other than using F2 and S3. And that's because you get trapped in psychological inertia. So that's the power of using Suffield analysis. I mean, the rules come from the laws of the evolution of technical systems, and they transform the system to the next generation system. Okay. All right, so why do we want to use it? Well, the 76 standard solutions I just said emanate from the laws of evolution, and they transform then to the next generation systems, okay, and get us out of this trap of psychological inertia. Oops. Okay, let's talk about now the knowledge base of effects. Supporting TRIZ is a whole database of physical, chemical, and geometrical effects, you know. So, I mean, if you've forgotten your chemistry or your physics from college and all those things, part of the database are various physical effects, chemical effects, and geometrical effects. For 250 physical effects, 120 chemical, and 50 geometrical effects. And these are very useful for solving problems.
I was just going to say, with that many effects, 420 of them, it would seem to me almost impossible not to be able to solve problems.
Right. There are more effects than that, but this gives you a tremendous list of things that you can incorporate in looking at the solution space in order to be able to solve a problem.
So they are widely used then?
Absolutely.
Clearly.
All right, so physical effects. Things like, for example, like there are 250 of them, but we just say things like thermal expansion for precision measurement or movement of materials. So if you know the coefficient of expansion, depending upon how much heat you apply, or bimetallic construction, you know how much a metal is going to bend by heat, all those kind of things, you can use those physical effects.
Like a thermocouple.
Like a thermocouple to get you a certain solution. Okay, so they universally can be applied to any kind of system. So the 250 physical effects.
We have a call from Deere Company.
John Deere?
Yes.
Okay, we have a caller, ladies and gentlemen, from the John Deere Company. Go ahead.
Yes, hello. My name's Sarkis Buklukian, and as I watch the presentation...
Excuse me, could you speak a little bit slower, please?
Okay. I have a question as I watch the presentation. Is there software which generates the solution pathways in that All-Schultes matrix and possibly enumerates the solution pathways to make this easier to apply?
Okay, the question, if I heard correctly, was dealt with the presence or absence, the availability of software to carry out the various procedures as enumerated by Steve here. I know the answer, but I'll let Steve answer. Go ahead.
Yes, there is software that's available. And you can call ASI to find out where you can get that software at. There are two different two different pieces of software out in the marketplace, and we'd be more than happy to talk to you about any one of them. But there is software available, and that's the exciting thing about TRIZ is that we don't have to use old books and manuals. This has been reduced down to a DOS-based and soon-to-be Windows-based software, and we can get to those technical and physical contradictions and principles, or the knowledge base of effects very, very quickly, and then start looking at examples of how they've been used. And so it really does improve the productivity of any engineering department, I would say by as much as a factor of 10x, and I'm not exaggerating.
Full order of magnitude.
A full order of magnitude. You know, when you start solving problems using this, I have seen tremendous improvements in productivity.
Okay. By the way, and I'm sorry I didn't catch your name when you called in, but the last night Steve and I had an opportunity to have dinner, and he was demonstrating for me one of the software packages that assists in the TRIZ activity, the TRIZ algorithm. And I've got to tell you, it's very, very user-friendly, very, very comfortable. It would seem to me that with very little prep, that an individual who was interested in using TRIZ or a team that was interested in using TRIZ could find it extremely valuable in getting the job done.
Okay, so in other words, it's not required to be a consultant-based system?
No, it's just like doing Taguchi methods or doing QFD or any other innovation or improvement methodology. You know, they can be done by hand, but they can be done more easily with the assistance of the computer.
Okay, thank you.
Sure enough.
Okay, thank you for the question.
And we continue on.
Okay, so we've got the physical effects. All right, there are chemical effects. Unfortunately, not all of us are chemical engineers like you, Jack, but...
Yay, Purdue.
There are 120 chemical effects, and we only see them about 1 in 1,000 used in inventions, but and that's primarily because we're not chemical engineers, and psychologically we're trapped out of looking for chemical solutions. But there are a number of them that we can use to solve problems, for joining things together, etching metal, all kinds of things we can do chemically. Then geometrical effects. There are over 50 geometrical effects, things like brush construction, spirals, Mobius strip, all of these things that we can use in order to solve a particular problem that we have. Various geometrical effects. All right, let's talk a little bit about now some of these other tools or operators of TRIZ, technological forecasting. This was Dan's question from Kodak earlier, essentially around this. revealing the current state of a system's evolution and then understanding where that system is relative to those 8 laws that we had talked about. And remember, those 8 laws are affinity headers for 200 sublines of evolution.
Yes.
Okay? So mapping them to where they're at within the context of those 8 laws. And then solving tomorrow's problems today. In other words, predicting future derivatives, or how is your product going to morph over time? How is it going to change? And then what are the things that you need to do today to solve problems? Now,
I was just thinking, you know, about this. You know, I think of this database of patents. You know, that what 1.5 million patents that have been searched out so far. Does this forecasting, is this also derived from that database?
Absolutely. Everything emanates from the database. Everything emanates from that database. But I was thinking that, you know, if we think in terms of what are the future derivative products going to look like, then if we want to do technology development, which Shin is going to be talking about in May, and you want to find out where you want to spend your R&D dollars today for the future technologies, this is a perfect marriage of that. You predict the technology, you predict the evolution of your product, and then you do technology development so that you have robust technologies on the shelf in order to be able to design those products.
And incorporate the voice of the customer, a la quality function deployment.
You got it.
And you know what, it sounds to me that the synergy of the 3 of those together really deserves a symposium all by itself. What do you think?
I think you're exactly right on. We may have something to say at the end of the...
Let's wait and we'll see. Okay.
Now, you know, actually, when you think about the 3 of those things together, what you really have are 3 independent systems that are now combining into a poly system, QFD, robust design, and TRIZ, that will convolute eventually into
a super system.
One super system.
That's right.
Exactly right. All right, so technological forecasting. So if you're thinking about creating strategic patent umbrellas and patent blockades, it's a very useful tool. Or if you have a blocking patent, in other words, if somebody is preventing you from using a certain technology, then one of the things you can do in TRIZ is to legally bypass, circumvent it with the next derivative evolution of that product.
And you've leapfrogged and left them in the wake.
Right. All right, another element of TRIZ is subversion analysis. In other words, these are deliberate attempts to create system failures. What do we have to do to subvert the product? And what I say, this is sort of the KGB answer to FMEA, or failure mode and effects analysis. I'll give you an example. Helicopter rotor blades were pitted occasionally, when they were trying to solve the problem, they couldn't find out what the root cause of the problem was. So the TRIZ specialist essentially said, well, let's make the whole thing pitted. What do we have to do in order to get pits across the entire helicopter rotor blade? And so when they microscopically analyzed the pits, they found out chemically what the substance was.
The cause, right.
The cause of it. And so they tried to subvert the product and get pits throughout the whole rotor blade. In that analysis, they were able to find out periodically where these rotor blades came into contact with that particular chemical, and that solved the problem.
Beautiful.
Yeah. So now, if you think in terms of technological forecasting coupled to subversion analysis, you know, what you're really going to be able to do is keep the liability engineers away from your product when the future products come out. And then if you've got that coupled to robust technology development, you're going to be world-class.
Yeah, you got quite a system.
You're going to be world-class. Okay, so here's a little summary. This is a scientifically based methodology. We've got 50 years of research that have gone into TRIZ. It is continually evolving. It's based upon, as I said, the 1.5 million patents. It overcomes psychological inertia. It uses very rigorous analytical techniques. That would be the ReVelle algorithm, and it moves us toward ideality. All right, and so what I have here now are then the 3 major things that are the operators that we have talked about: substance field analysis, the ReVelle algorithm, and then resources. And the intersection between substance field analysis and ReVelle, again, essentially gets us to what?
Our physical characteristics.
Physical contradictions.
Contradictions.
Contradictions, right. Physical contradictions, okay? And the intersection between ReVelle and the use of resources moves the system toward
Ideality.
or higher signal-to-noise ratio in the system, and the intersection between resources and substance field analysis gets us to using the physical,
Effects there.
chemical, and geometrical effects, and then the intersection of all of these is what we're calling TRIZ or TIPS.
Right, the theory of inventive problem solving.
Right. All right. So what we're saying is next generation product development really, a good friend of ours, Dr. Jim Kwolek from the Renaissance Leadership Institute in Oregon House, California, calls it triads. And he's already done some work on this. But we're saying next generation product development is a combination of QFD, TRIZ or TIPS, and then robust design technology development. And we'll have something to say about the conference. Okay, integrating with QFD. Very quickly, I'm going to, many of our listeners and viewers are familiar with quality function deployment, taking the what's and translating those into hows or the measures. And then what we come up with in the roof of the house of quality here are the conflicts with the X's and the double X's. And that, in essence, in TRIZ is a physical contradiction. Now, in the past, we've sort of thrown our hands up, but now we're going to be able to go into the contradiction tables and or the separation principles. The other element we want to look at is where we really need to get some sort of technological breakthrough, get the next generation system. So that's how it integrates with TRIZ.
You know, Steve, I'm looking at the clock, and I see we've only got just over 2 minutes left. Before we complete these visuals you got, I think it's important that we share with our audience this opportunity that they're going to have this coming November with the American Supplier Institute sponsoring the first annual QFD Robust Design Symposium here in the Detroit, Michigan area with a focus not only on QFD and robust design, but on TRIZ as well. Could you tell the folks just a little bit about that?
Yes, on November 1st, 2nd, and 3rd at the Ritz-Carlton in Dearborn, Michigan, we're going to have a symposium, and Dr. Taguchi is going to be there. We're going to attempt, or I'm going to ask our good friend Jim Kwolek, who's going to be traveling to Russia, to invite Altshuler. Whether or not he can come, we don't know.
You understand he's got a health problem.
He's got a health problem. But I think it would just be fabulous to get two of the brightest minds alive in the world today at one place at one time. But whether or not that's possible with Altshuler, I don't know. But we are going to then have a series of very good case studies and or tutorials that are going to be delivered on this subject and showing the integration of all these, which we think is the next generation for developing new products and or solving current problems.
Outstanding. That sounds like a real opportunity for our viewers and their professional colleagues to participate in a really unique event. First ever opportunity to bring together all these technologies in a single place, looking at quality function deployment, both basic and advanced, robust design, basic and advanced, and a look at TRIZ and how it integrates together to form the triads. You know, I hate to do this to you, Steve, but we've only got about 20 seconds left, and so I guess I'm going to have to wrap this up. There's only 3 or 4 visuals that we've got to look at. So let's, you know, you've got it up on the screen there. You can see that the Ritz-Carlton in Dearborn, Michigan is the location, November 1st through the 3rd. You've got the phone number, if we can get that last slide, that has the ASI phone number on it coming up. We'll see you all in just 1 month. I'll be back with Peter Schultes from the University of Wisconsin at Madison talking about teams and why we work together. Steve, thank you very, very much for being here. Outstanding presentation.
Thank you, Jack.